Welcome to AP Physics Made Easy. My name is Eric Sampson, and if you're looking for a little help understanding the subject matter, you've come to the right place. Today we're going to look at some basic measurements called distance, displacement, speed, and velocity. They're easily confused with each other, but I'm going to help you get them sorted out. Let's just go ahead and jump right in. So let's start with this. Let's just say I've got my friend here, and he suddenly realizes, oh my gosh, I don't know where my phone is. Maybe I left it over here. So he walks 10 meters to the right and looks down and realizes, nope, I don't see my phone here. And then they go, wait a second, maybe it was 30 meters over to the left where I left it. And there it is, and he gets his phone back. Aren't we happy about that? So we can talk about the distance or the displacement that happened here. So let's just talk first about distance. This is something that we're very familiar with in our day-to-day lives. Distance is basically how far the object, in this case the person who lost his phone, how far the object has traveled. Now, this is a scalar quantity, which means that there's no directional aspect to it. It's blind to the direction. And in this case here, surprise, surprise, the person traveled 40 meters, right? He went 10 meters to the right, he went 30 meters to the left, total distance of 40 meters. It's what we're used to thinking of, like when we go on a hike or whatever. But displacement is something different, and displacement is much more important in physics. So displacement is not how far the object traveled, but how much its position has changed. We call this delta x. Delta always means change in, and change is always defined to be the final position minus the initial position, at least for delta x. So delta always means final minus initial. Now, it is a vector quantity. Now, hopefully you watched my video on vectors versus scalars. So a vector quantity has a directional component to it, and we usually use a positive or negative sign to indicate which way the object, in this case, has been displaced. So in this case here, the person or object started off in position A and ended up, that's the initial position, and ended up 20 meters to the left of where he started, and we're going to call left to be the negative direction. So the displacement is negative 20 meters. And notice that's very different from the 40 meters distance that the person's traveled. So we definitely need to get good at understanding how to calculate displacement and when to use it. Now let's talk about speed versus velocity. Again, speed is something that we typically think of in our day-to-day lives. Velocity we think we do, but most of us don't. Let me show you what I'm talking about here. So let's just say the time to complete this journey was 8 seconds. So, which is kind of fast, but whatever. Okay. So let's talk about the average speed. The average speed, and we'll use this equation here. So the average speed is just the distance traveled divided by the time of travel. You probably did this in a math class many years ago, right? Probably in elementary school. So the average speed is just the distance traveled divided by the time. So in this case here, I'm just going to substitute in the distance traveled we decided was 40 meters. It took 8 seconds. So the average speed would be 5 meters per second. All right. Now, because obviously like the person wasn't traveling this speed the whole time because they stopped and looked, whatever. But on average, between here and here, we'd say their average speed was 5 meters per second. Well, let's see what happens when we talk about the average velocity. Well, the average velocity equation looks a lot the same, except instead of saying the distance, we're going to say the change in position, the delta x, over the change in time. Now, in this case here, we've said that from last one, we saw the person's displacement. They ended up 20 meters in the negative direction from where they started. So their displacement was negative 20 meters. It took 8 seconds for that total change to occur. So their average velocity is actually negative 2.5 meters per second. And notice that's very different from what we found for positive 5 meters per second of speed. All right. Now the thing is, it's easy to confuse them because they're both measured in meters per second. And the truth is, we will almost always talk about velocity in physics, and we'll very rarely talk about speed, except that we often use the word speed to simply refer to the magnitude of this vector. All right, let's keep going then. Now, I want to talk about the difference between average velocity and instantaneous velocity, because these equations have been giving us the average velocity or average speed. But in physics, we're more often interested in the instantaneous velocity. So let's say I have a car here. At time t equals 0, it's parked. The light turns green, and I find 1 second later the car is going 5 meters per second. After 3 seconds, the car is going 15 meters per second, and all in the positive direction, by the way. And then it sees another red light, it stops, and at t equals 4 seconds, it's come to a stop again. So the total distance traveled, let's just say, was 20 meters. So the average velocity, we would say, all right, how much has it displaced? Well, it displaced 20 meters in the positive direction. It took 4 seconds, we'll say. Here's 4 seconds. So it gives us 5 meters per second in the positive direction is its average velocity. But the thing is, most of the time, this car was not going 5. Look, it was going 5 here at t equals 1 second. But after that, it was going 6, 7, 8, 9, all the way up to 15. So it only for one brief moment in time was going 5. And then between 15 and 0, it had to pass through 5 again. So at 2 points along the way, it was actually going at the average speed. But most of the time, it was going some other value. So these other values are known as the instantaneous velocity. That's how fast you're going at a given moment in time. And that's actually what we'll work with more in AP Physics 1. So at time 1, the instantaneous velocity was 5, but at time 3, the instantaneous velocity was 15. And because the magnitude of the instantaneous velocity is the same as the value for the instantaneous speed, that's why we often use the word speed in lieu of saying velocity, but it's just something you got to get used to. All right, let's try this one here. So I have a bug that's going to fly in 2 different dimensions, okay? We'll say we're looking down on it from above. So what we find is I want to find the distance the bug traveled, and I want to find the average speed of the bug. So the bug does this. The bug flies 8 meters to the east, then 6 meters north, then 10 meters to the west, and finally 4 meters to the south. And it took 8 seconds for this to happen. So let's determine the distance the bug traveled. Well, to find the distance, all I have to do is sum up all those different segments. So 8 plus 6 plus 10 plus 4, that gives us 28 meters of distance traveled by the bug. And it took 8 seconds, so if I want to find the average speed, I just take the distance traveled and divide it by the time, and I get 28 over 8, and that's going to give me an average speed of 3.5 meters per second, and I don't indicate which way. Obviously, the bug traveled lots of different ways. Okay, let's look at the same scenario, but this time let's determine the bug's displacement and average velocity. So we have the same scenario, the 8, 6, 10, 4. So what we're going to do is, in order to find the net displacement, if you recall from the video we did on vectors, we're just going to use what's called the tip-to-tail method. So basically, at the tip of this one, I put the tail of this one, and so I've already got them set up using the tip-to-tail method. Well, what happens then is I want to find the resultant vector. So remember, when you're using the tip-to-tail method and you want to find the resultant or net vector, you start where you started and you draw a line that ends where you ended, and I get this is my resultant vector. So I'm going to then break this resultant vector up into 2. So I don't know how long this is. So the way I'm going to find it is I'm going to find 2 component vectors. I'm going to find the x component and the y component. So here's the x component, and I see that's negative 2 meters. And I have to indicate the negative because I'm dealing with vectors now. So this is the negative direction left. And then up is going to be the positive direction, and that's 2 meters in the positive direction here. And so therefore, if I want to find the resultant vector, I just use Pythagoras, and I'm going to solve for the resultant vector. So the square of the resultant is equal to this square plus this square. So I'm just going to skip a step and go here. I'm going to substitute in the values for x and y, and I see that the resultant vector is 2.8 meters to the northwest, we're going to say. Now, we could also learn later on how to use angle values for this, but right now we're just going to say to the northwest. Well, what about its average velocity? Well, the average velocity is just going to be the displacement, which is delta x, divided by the time, and the time in this case is still 8 seconds. So we're just going to say 2.8 meters to the northwest divided by 8 seconds. So I get 0.35 meters per second to the northwest. As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that, or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.